our key focus today is on some certain kinds of proportional relationships. Of course, these are all going to come from similar figures, so knowing that two shapes are the same size through angle-angle, through side-side-side similarity, through side-angle-side similarity, through movement, somehow we know that these two shapes are similar. In order to make indirect measurements, essentially we're just saying, instead of actually putting a ruler down and measuring something, instead of actually getting in a car and driving a distance, we can measure how long something is by setting up a proportion based on similarity. That's all we're focusing on. The kinds of indirect measurements that we're very focused on, and the ones that are of the most importance for us, regard perimeter and area. Essentially, we've seen time and time again that based on different kinds of pictures, we're able to use similarity to set up proportions, solve the proportion to get our answer. Our key focus today is knowing how to set up the proportion so that we can figure out perimeter and we can figure out area. All right, so this is the standard kind of problem that we've already been doing. Student who's 5'6", standing near a pole. Well, they've got shadows on the ground. Figure out how tall the flagpole is. Well, it's fairly easy to measure the height of a person because it's not like crazy big, but if you want to measure a flagpole, what are you going to do? Climb up to the top and then throw a ruler down? That's not a very effective method. Indirect measurement will allow us to use these similar triangles and create a proportion to figure out that answer. And of course, we always know that we'll just match pieces up. 5 feet has to match up with 14 feet. So we'll say 5 feet matches up with 14 feet 2 inches. 5'6" then has to match up with the height of the pole. There's our proportion. And now we have a problem. In all of our similarity problems that we've been doing, we haven't had an issue where we've had two labels. Feet on the left does not match mixed feet and inches. This is a problem that we need to fix before we can get our answer. The geometry part is already done. We've set up the proportion. Now we just have to do some algebra and arithmetic. Well, you have a choice. Do you want to change everything to inches, or do you want to change everything to feet? It's up to you. And after taking a quick look in class, they wanted to go with inches, so let's set up our conversion then. How do you change 5 feet into inches? 5 times 12, and I want to change this to blue. Hey, come on, I want blue here. Give me blue. There we go. 5 times 12 would give us 60 inches. 5 feet times 12, 60. Add on that extra 6. That's 66 inches. 14 times 12. 14 times 12 equals 168. 168 plus this extra 2 inches, that's 170. And so, here we go. We just now need to solve this proportion, and we will have our answer, the height of the flagpole as measured in inches. All right, and we know that we can solve a proportion with cross multiplying, so 60 times h. And if anyone has a calculator handy, we can speed up some of our number crunching. 66 times 170. Okay, so 66 multiplied by 170 gives us 11,220. And divide out by 60. We have our answer that it is 187 inches tall. Hooray, we're happy. The height of the flagpole is 187 inches. How big is 187 inches? Of course, it's not really a typical thing for people to look around and say, oh yeah, check that out. That car is clearly 412 inches long. Or that boat is 412 inches. The last thing, of course, we have to do is to convert this back into feet. Just divide by 12 then. So when we divide by 12, we've got 15.5 feet. And we've discussed earlier in the year that with this piece, we can figure out how many inches that would be. If we subtract off our 15 and multiply by 12, that's going to tell us how many extra inches there were. This was 15 feet and 7 inches. So here we go. That's how tall that flagpole would be. And we're done. This process collectively is referred to as indirect measurement, because we're getting the measurement of something, but we're not putting a ruler down to measure it correctly. We're using similar figures. A really common place you encounter these are scale drawings, like in maps. So on a Wisconsin road map, Kristen measured a distance of 11 1/8 inch from Madison to Wausau. The scale on the map is 1 inch to 13 miles. 1 inch on the map represents 13 miles in real life. What's the actual distance between them? Okay, so 11 1/8 inch will represent some unknown number of miles. And of course, we can look at this now, and we recognize that our labels are matching. Inches matches inches, miles match miles, so we can go directly to cross multiply. So 1 times x, sweet, 13 times 11 1/8. Okay, and we know we can enter these into our calculators pretty easily. 13 times multiplied, and mixed numbers have to be put in a parentheses. 11 and 1/8. 13 multiplied by 11 1/8. 144.625. Again, we want this as a mixed number, so we've already got the 144 miles. And what we could do then, we multiply this off. 0.625 is what? As a fraction. Some people have its memorized form down. If we were to simply take 625 and put it over 1,000, of course that's just the decimal 0.625, so if we go over and simplify 625 over 1,000, we could get our answer in our preferred mixed number form. Of course, you could divide by 5, you could divide by 25, you could divide by their common factors, and when you eventually divide that down and simplify it, you will get 5/8. Of course, being a proper nerd, I've got that memorized. And there, we're done. You'll notice neither of those were based on our perimeter and area, which I mentioned are the most important ones. We'll get to those. Each of these are simply word problems for the types of similarity that we've already been doing. Same thing on this one. This one actually asks us to draw a scale drawing. Lady Liberty holds a tablet in her left hand. The tablet is actually 7.19 meters long, 4.14 meters wide. If you are going to use the scale, 1 centimeter to 3/4 of a meter, what would the dimensions be to the nearest tenth? This is going to require 2 steps, or 2 stages. With it being 7.19 meters long, you could figure out how many centimeters long it would have to be. Solve our proportion, and you get the answer for how long it is. Using the exact same scale, because of course the scale doesn't change, we can figure out how wide it needs to be by setting up a second proportion. We need to solve both of them. And once we've solved both of them, we know what dimensions we would have to have, so let's run through. 0.75, 1 times 7.19, and we know that we just have to divide by 0.75, so 7.19 divided by 0.75. Okay, so rounding to the nearest hundredth of a meter, or the nearest hundredth, we would say that is approximately, our directions say rounded to the nearest tenth. To the nearest tenth, 9.58 would round to 9.6. Okay, that would have to be 9.6 centimeters long. Same thing, 0.75 times y, 4.14. And with that division, 4.14 divided by 0.75, 5.5, rounded to the nearest tenth. There, we're done. This set of directions did not actually ask us to physically draw it. The directions only asked what would the dimensions be. You will have problems, though, that say, I want you to actually make the drawing. Having done the math, we know how big they would need to be, and so our next task is to simply take a ruler, and when the directions say we want you to draw, then you simply take a ruler and actually draw it. So we need 9.6 centimeters. Got our centimeter side. 9, 9.1, 9.2, 9.3, 9.4, 9.5, 9.6. And I got a little bit long on me. That actually got over to 9.7 because of my board. So 9.6. And it's still going over. This may be a computer thing where it's not letting me stop at 9.6. Okay, there, I got 9.6. So there's my long. And with that, we can then rotate it to get how wide it is, which I need 5.5. So, no, move down on me. 1, 2, 3, 4, 5. 5.1, 2, 3, 4, 5.5. Bring it over. Rectangle, we'll get another 5.5. And I can just connect them. There we go. At 9.6 centimeters and 5.5 centimeters, this is a scale replica of the tablet that the Statue of Liberty holds. Of course, the tablet is vertical. It doesn't have this orientation. But we're done. We can create scale drawings. Finally, we get to the piece that I mentioned was the most important characteristic, because this is the new material. Each of the things that we were doing before are based entirely on similarity. There's nothing new there. They were just word problems based on the similarity that we've already been doing. This is the new material. So far, when we set up our similarity ratios, we were always finding one length. What is the one missing side? Well, we can actually set up similarity based on our scale factors, based on our similarity ratio. And that will allow us not to figure out just one side length, but all the side lengths added together, or the entire area. And if you'd like to pause and finish writing these pieces down, you can. Rather than go through and simply state the pieces, I want to show you how you would do it with a word problem within the problem, because it actually is easier to understand when you see a physical example as opposed to reading the theorem. All right, so with our example, here's what we're seeing. We have a pair of similar triangles. Figure out the perimeter, figure out the area. Of course, you can look at these pieces and see right away 13 is going to correspond with 9.1. We are able to create a ratio of 13 to 9.1, no problem. To figure out this perimeter, well, you'll notice right here, we are told the perimeter of the big triangle is 36 centimeters. We want to know what is the perimeter of the small one. We can set it up exactly the same way that we have. Big triangle, small triangle. That's the geometry. Same way that we've been doing all our proportions, same way. Find the pair of things that go together and then create the proportion. So we will multiply 13 times p, 60 times 9.1. Okay, that would equal 546. All right, and we're backing up because Chance helped me out, and says I can't cry. You looked at the wrong number. He's absolutely right. I wrote down 60 for the area, and we're doing the perimeter problem, so my brain was dumb there for a second. It even said right in the video, it's like, hey, it's 36, and then I didn't write down 36. Okay, our perimeter is 36. So 13 times p, and then 9.1 times 36. Okay, 327.6. 327.6. Of course, we'll divide out by 13. And that gives us then the perimeter of that smaller triangle. Divide out by 13. There we go, 25.2. So pretty straightforward. Same thing as what we were doing before. Area is going to work similarly with one added twist to it. We will still start off with our matching pieces. 13 is still going to match up with 9.1. And then we can still build our area with area, but there's a problem with this. In particular, this scale factor that we've created was based on matching up lengths with lengths. It was based on matching up centimeters to centimeters. Area does not have a label of centimeters. Area has a label of centimeters squared. And so this is actually the wrong kind of scale factor. This is the wrong similarity ratio. It works for lengths, it doesn't work for area. Fortunately, we've got a really easy fix for that. To turn centimeters into centimeters squared, you just have to square it. That's exactly what we're going to do on the left-hand side of our proportion. In order to handle this with area, we're just going to square these things. That's it. By squaring both of them, now we've got an appropriate ratio. Now we can cross multiply and solve. It's the exact same work after we've squared. So we'll go through, and 13 squared equals 169. 9.1 squared, 9.1 times 9.1, 82 and 81 hundredths. And we're all set. 169 times area, 82.81 times 60. So 4,968.6. 4,968.6. Divide out by 169. And we've got it, 29.4. Making sure we get the correct label on it. Centimeters squared. We're done. It's very, very common for students to forget this process. Anytime you're working with area, you have to remember this scale factor will need to be squared. I'd also like to note, later on in the year, we're going to get into our 3D shapes unit where we're working on volume and we're working on surface area. We will come back and do these types of things again when we're working with volume, where we could have a small cube and a big cube, or a small sphere and a big sphere. When we have similar 3D shapes, and we want to do this exact same process with volume, since volume has a label of centimeters cubed or feet cubed, what do you think you would wind up doing here? We will do this exact same process, but instead of squaring for area, we will cube for volume. It works the exact same way. So we will come back and see this again with our later units. Thus, this finishes off everything we needed. You'll note we've seen how you can set up a proportion to figure out perimeter, how you can figure out area, and we've seen that you can set up proportions so that we can take indirect measurements. They're all just further applications of having similar figures.